In this example, we're going to approximate the area under the graph of g of x equal to a negative 0.02 x to the fourth plus 0.28 x cubed minus 0.3 x squared plus 20 over the interval 2 to 12 using 5 subintervals. I want to begin by taking a look at what the graph of this function looks like so we get an idea of what we're working with. So now in our graphing calculator, we're going to select y equals, and we're going to type our function into our graphing calculator. You may pause the video for a second to do that if you want to follow along. And then you're going to hit Windows, and we're wanting to approximate the area over the interval 2 to 12. So I've changed the x min to be 2 and the x max to be 12. And then after a little trial and error, we can see our entire function if we set our y max to be 80 to see it over this interval. Alright, next we're going to hit graph, and there is the graph of our function from the interval 2 to 12. And our goal here is to approximate the area under this curve using rectangles. And we're going to divide this up into 5 subintervals. Next, what I'm going to do is make a rough sketch of the graph that we just saw in our graphing calculator. And a rough sketch looks something like this here. And we're interested in calculating the area under the curve between 2 and 12. Now notice the shape of this figure between x equal 2 and x equal 12. Notice it's not a geometric shape like a rectangle or a triangle for which we can actually calculate the area of. So the best we can do for now is approximate it by creating rectangles that fit within this area or close to this area. Now what we're going to do first is we're going to figure out what our delta x is. Now our delta x gives us the width of each rectangle, and we calculate that by subtracting our endpoints. So we're subtracting 12 minus 2, and then we're dividing it by n, where n is the number of subintervals. So here in this problem, we're told to use 5 subintervals. So that's what n is equal to. So we're dividing by 5. So 12 minus 2 is 10, so we have 10 over 5, which is 2. So the width of each rectangle is going to be 2. So next what we can do is draw our rectangles on our graph so we get a visual of what we're doing here. With a width of 2 means that each rectangle has a width of 2. So from 2 to 4 is our first rectangle, and then from 4 to 6 is our next rectangle. 6 to 8 is the next one, and then 8 to 10, and then 10 to 12. Now in these examples, we're going to be using the left side of the rectangle, the left endpoint, to calculate the areas. And that's kind of an arbitrary decision. We could use the right endpoint, or in some cases use the midpoint, but for these examples, we will be using the left endpoint. And in your homework, they will indicate to use the left endpoint. So using the left side of this rectangle, that's the height of the rectangle for the first rectangle. And then the left side for the second, the left side for the third, and by using the left side, that gives us the height of each rectangle. There is the left side, going from the left side of the fourth rectangle, and then the left side of the fifth rectangle. So here let's shade in our rectangles. So now notice if we calculate the area of these 5 rectangles, it'll give us an approximation for the area under the curve from 2 to 12 along that subinterval. Notice it won't be an exact, but it'll be a good approximation. We should also notice that the more rectangles we use, the better approximation that we're going to get. Now the area of the region under the curve is approximated by the sum of the areas of the rectangles, and we can express that using summation notation, which looks like the following. We use our summation symbol from I equal 1 to n. In this case our n is 5, where we take the function at each of the x sub i's, which are going to be these x sub i's here, times delta x, which is the width of each rectangle. The width of each rectangle in this case is 2. So this gives us the width of each rectangle, whereas our function value at each of these x sub i's is going to give us the height of each rectangle. And then we're going to sum all those up. So we're going to have 5 terms here in our summation, where each term represents the area of each of the 5 rectangles. Now this is kind of the general formula that we use for summation notation to calculate the area of these rectangles. In this case, our function is g, so we should modify this to be g instead of f. And then also, as I said, we're summing from I equal 1 up to I equal 5. So let's fix that as well and change n to be 5. Next, let's write out each of our 5 terms for this summation notation. So there's what our sum looks like when we expand it out from the summation notation. Notice how each one of these terms in our sum here represents an area of one of these triangles. I should also point out that 2 in this case, when x equals 2, that is our x sub 1. And then 4 is our x sub 2, 6 is our x sub 3, 8 is our x sub 4, 10 is our x sub 5. Those are the left endpoints for each of our rectangles. Now when we calculate this summation, we know that our delta x is 2, but we need to calculate our function g for each of our left endpoints. So that's going to look like g of 2 times 2 plus g of 4 times 2 plus g of 6 times 2 plus g of 8 times 2 plus g of 10 times 2. We can use our calculator to make it quicker to calculate each of these function values. So g of 2 is 20.72. When we plug 20 into our g function, we get 20.72, and then that is times 2 plus g of 4. And g of 4 is 28 times 2 plus g of 6. G of 6 is 43.76. That's being multiplied by 2 plus g of 8. When we plug 8 into our function, we get 62.24 times 2 plus our last term, so g of 10. Plugging 10 into our function, we get 70 times 2. Alright, and then calculating all of that, we get a total of 449.44. So that gives us the approximation for the area under the curve between 2 and 12 for this function g of x.